Induction motors are the most widely used alternating current motors. They operate on the principle of electromagnetic induction. In an induction motor, a changing magnetic field in the stator induces a current in the rotor, which then produces its own magnetic field. The interaction of these two magnetic fields creates torque, causing the rotor to spin. These motors are robust, relatively inexpensive, and require minimal maintenance, making them suitable for a wide array of applications. Common uses include pumps, fans, compressors, and various industrial machinery. The stator of an induction motor houses the main windings that, when energized with alternating current, produce a rotating magnetic field. The rotor can be either a squirrel cage type, consisting of conductive bars shorted at the ends, or a wound rotor type, with windings connected to slip rings. Squirrel cage rotors are more common due to their simplicity and durability. The speed of an induction motor is determined by the frequency of the alternating current supply and the number of poles in the stator winding. The synchronous speed is calculated as 120 times the frequency divided by the number of poles. However, the actual rotor speed is slightly less than the synchronous speed, and this difference is known as slip. Induction motors are generally classified into single-phase and three-phase types. Three-phase induction motors are more efficient and produce higher starting torque compared to single-phase motors. Single-phase induction motors require a starting mechanism, such as a capacitor start or split-phase configuration, to initiate rotation. For direct current motors, permanent magnet direct current motors are quite prevalent. These motors use permanent magnets to create the magnetic field necessary for operation. The interaction between the magnetic field of the permanent magnets and the magnetic field produced by the current flowing through the armature windings generates torque, causing the motor to rotate. Permanent magnet direct current motors are valued for their high efficiency and excellent speed control capabilities. They are commonly used in applications where precise speed control is required, such as in robotics, automotive systems, and consumer electronics. The speed of a permanent magnet direct current motor is proportional to the applied voltage and inversely proportional to the magnetic field strength. By varying the voltage applied to the armature, the speed of the motor can be precisely controlled. The torque produced by a permanent magnet direct current motor is proportional to the armature current and the magnetic field strength. Permanent magnet direct current motors offer several advantages over other types of direct current motors, including higher efficiency, smaller size, and simpler construction. They eliminate the need for field windings, reducing copper losses and improving overall efficiency. However, permanent magnet direct current motors may be more expensive than other direct current motor types due to the cost of the permanent magnets. Additionally, the strength of the permanent magnets can be affected by high temperatures or strong demagnetizing fields, which may limit their use in certain applications. When selecting a motor for a specific application, several factors must be considered, including the required torque, speed, efficiency, and environmental conditions. Induction motors are generally preferred for applications requiring high power and continuous operation, while permanent magnet direct current motors are often chosen for applications requiring precise speed control and high efficiency. Other types of alternating current motors include synchronous motors and universal motors. Synchronous motors operate at a constant speed determined by the frequency of the alternating current supply and are used in applications such as timing devices and power factor correction. Universal motors can operate on both alternating current and direct current and are commonly used in handheld power tools and appliances. Other types of direct current motors include series motors, shunt motors, and compound motors. Series motors have high starting torque and are used in applications such as electric vehicles and cranes. Shunt motors have relatively constant speed and are used in applications such as lathes and fans. Compound motors combine the characteristics of series and shunt motors and are used in applications requiring both high starting torque and stable speed. Motor efficiency is an important consideration in many applications as it affects the energy consumption and operating costs of the system. High-efficiency motors can significantly reduce energy consumption and lower operating costs over the lifespan of the motor. Motor efficiency is typically expressed as a percentage and is defined as the ratio of mechanical output power to electrical input power. Factors that affect motor efficiency include motor design, operating conditions, and load. Proper motor maintenance is essential for ensuring reliable operation and prolonging the lifespan of the motor. Regular maintenance tasks include lubricating bearings, inspecting windings for damage, and cleaning the motor to prevent overheating. Overheating can significantly reduce motor lifespan and lead to premature failure. Motor protection devices, such as overload relays and fuses, are used to protect motors from damage due to overcurrent or overvoltage conditions. These devices automatically disconnect the motor from the power supply in the event of a fault, preventing damage to the motor and other equipment. Variable frequency drives, also known as adjustable speed drives, are used to control the speed and torque of alternating current motors. Variable frequency drives work by varying the frequency and voltage of the power supply to the motor, allowing for precise control of motor speed and torque. They are commonly used in applications such as pumps, fans, and conveyors to optimize energy consumption and improve process control. Motor selection also depends on the load characteristics. Constant torque loads, such as conveyors and positive displacement pumps, require motors that can provide constant torque over a wide speed range. Variable torque loads, such as centrifugal pumps and fans, require motors that can provide varying torque depending on the speed. Understanding the load characteristics is crucial for selecting the appropriate motor for a given application. Motor enclosures are designed to protect the motor from environmental factors such as dust, moisture, and corrosive materials. Enclosure types include open drip-proof, totally enclosed, fan-cooled, and explosion-proof. The selection of the appropriate enclosure type depends on the environmental conditions in which the motor will be operating. Open drip-proof enclosures are suitable for indoor applications where the motor is protected from dripping liquids. Totally enclosed fan-cooled enclosures are suitable for outdoor applications or environments where the motor is exposed to dust or moisture. Explosion-proof enclosures are required for applications where flammable gases or vapors are present. Motor starting methods are used to limit the inrush current when a motor is started. Direct online starting is the simplest starting method, but it can result in high inrush currents that can cause voltage dips and damage to the motor and other equipment. Reduced voltage starting methods, such as autotransformer starting and part winding starting, are used to reduce the inrush current during motor starting. These methods reduce the voltage applied to the motor during starting, limiting the inrush current. Soft starters are electronic devices that gradually increase the voltage applied to the motor during starting, providing smooth and controlled acceleration. They are commonly used in applications where smooth starting is required, such as in conveyors and pumps. Motor braking methods are used to quickly stop a motor. Dynamic braking involves dissipating the motor's kinetic energy as heat in a resistor. Regenerative braking involves converting the motor's kinetic energy back into electrical energy and feeding it back into the power supply. Plugging involves reversing the motor's polarity to quickly stop the motor. Mechanical brakes use friction to stop the motor. The selection of the appropriate braking method depends on the application requirements and the desired stopping time. Motor standards, such as those developed by the National Electrical Manufacturers Association, define the performance characteristics and dimensions of motors. These standards ensure that motors from different manufacturers are interchangeable and meet certain performance requirements. The National Electrical Code provides guidelines for the installation and wiring of motors to ensure safe and reliable operation. The NEC covers topics such as motor overcurrent protection, motor disconnecting means, and motor grounding. Proper motor installation and wiring are essential for preventing electrical hazards and ensuring reliable motor operation. The most common alternating current motor is the induction motor, due to its robustness, cost-effectiveness, and versatility. The most common direct current motor is the permanent magnet direct current motor, favored for its efficiency and speed control capabilities. Both types of motors play critical roles in a wide range of applications across various industries. Understanding the principles of operation, advantages, and limitations of each motor type is essential for selecting the appropriate motor for a specific application. Factors such as torque, speed, efficiency, environmental conditions, and cost must be considered when making a motor selection. Proper motor maintenance, protection, and control are crucial for ensuring reliable operation and prolonging the lifespan of the motor. Utilizing variable frequency drives and soft starters can optimize energy consumption and improve process control. Adhering to motor standards and the National Electrical Code ensures safe and reliable motor installation and operation. The advancements in motor technology continue to drive innovation in various industries, leading to more efficient and reliable motor designs. Permanent magnet synchronous motors are gaining popularity due to their high efficiency and power density. Switched reluctance motors are also being developed for applications requiring high torque and variable speed control. As technology evolves, new motor designs and control strategies will continue to emerge, further expanding the capabilities and applications of electric motors. The proper selection, installation, and maintenance of motors are essential for ensuring the reliable and efficient operation of electrical systems. Understanding the principles of operation and the factors that influence motor performance is crucial for engineers and technicians working with electric motors. Continuous learning and staying updated with the latest advancements in motor technology are essential for maximizing the performance and lifespan of electric motors. Whether it is an induction motor driving a pump or a permanent magnet direct current motor controlling a robot, electric motors are the workhorses of modern industry and play a vital role in our daily lives. The ubiquitous nature of electric motors underscores the importance of understanding their principles of operation and the factors that influence their performance. As technology continues to advance, electric motors will continue to evolve and play an increasingly important role in shaping the future of industry and society. For example, the efficiency standards are set by organizations like the Department of Energy. These standards mandate minimum efficiency levels for certain types of motors. These regulations aim to reduce energy consumption and greenhouse gas emissions. Motor manufacturers must comply with these standards to sell their products in certain markets. The Energy Policy Act of 1992 and subsequent regulations have significantly impacted motor design and efficiency. These regulations have driven the development of more efficient motors and have led to the phasing out of less efficient motor designs. Compliance with these standards is essential for motor manufacturers and users alike. Furthermore, the National Electrical Code, or NEC, provides guidelines for the safe installation and wiring of motors. Article 430.1 covers motor circuits, motor overload protection, motor disconnecting means, and motor grounding. Proper installation and wiring are essential for preventing electrical hazards and ensuring reliable motor operation. Adherence to the NEC is mandatory for all electrical installations in the United States. Specific NEC tables, such as Table 430.250 and 430.251, provide full load current values for alternating current and direct current motors. These tables are used to determine the appropriate size of conductors and overcurrent protection devices for motor circuits. These values are based on the motor's horsepower rating and voltage. The NEC also specifies requirements for motor overload protection. Overload protection devices, such as thermal overload relays, are designed to protect motors from overheating due to excessive current. These devices trip the motor circuit when the current exceeds a certain threshold, preventing damage to the motor. The NEC also requires that each motor have a disconnecting means to isolate the motor from the power supply for maintenance or repair. The disconnecting means must be readily accessible and must be capable of being locked in the open position. Grounding is another critical aspect of motor installation. The NEC requires that motor frames be grounded to prevent electrical shock hazards. Grounding provides a low impedance path for fault current to flow back to the source, causing the overcurrent protection device to trip and de-energize the circuit. Proper grounding is essential for ensuring electrical safety. In addition to the NEC, other standards and regulations may apply to motor installations. These may include local building codes, environmental regulations, and industry-specific standards. Compliance with all applicable standards and regulations is essential for ensuring the safe and reliable operation of motor installations. The use of variable frequency drives, or volts per hertz, to control motor speed and torque can also affect motor efficiency and performance. Variable frequency drives allow for precise control of motor speed, which can optimize energy consumption and improve process control. However, variable frequency drives can also introduce harmonics into the power system, which can reduce power quality and increase losses. Proper filtering and harmonic mitigation techniques may be required to minimize the impact of variable frequency drives on the power system. Motor maintenance is also an essential aspect of ensuring reliable motor operation. Regular maintenance tasks include lubricating bearings, inspecting windings for damage, and cleaning the motor to prevent overheating. Overheating is a common cause of motor failure and can be prevented by ensuring adequate ventilation and keeping the motor clean. Vibration analysis is another useful tool for detecting potential motor problems. Vibration analysis can identify imbalances, misalignments, and other mechanical issues that can lead to motor failure. Regular vibration monitoring can help prevent costly downtime and extend the lifespan of the motor. Furthermore, insulation testing is essential for assessing the condition of motor windings. Insulation testing involves measuring the resistance of the insulation between the windings and ground. A low insulation resistance indicates that the insulation is deteriorating and that the motor is at risk of failure. Regular insulation testing can help identify potential problems early on and prevent catastrophic motor failures. In summary, the selection, installation, and maintenance of motors are complex processes that require careful consideration of various factors. Understanding the principles of motor operation, the applicable standards and regulations, and the proper maintenance techniques is essential for ensuring the safe, reliable, and efficient operation of motor installations. By following these guidelines, engineers and technicians can maximize the performance and lifespan of electric motors and minimize the risk of motor failures. These practices also help to ensure compliance with regulatory requirements and promote energy efficiency. The ongoing advancements in motor technology, coupled with the increasing focus on energy efficiency and sustainability, will continue to drive innovation in the field of electric motors. Staying updated with the latest developments and best practices is essential for professionals working with electric motors.